Hello everyone! Previously we have designed and built a Potentiostat circuit. Now we are going to program our microcontroller to perform electrochemical measurement like cyclic voltammetry. Let's go. In Potentiostat, we will apply various voltages to the electrochemical cell and measure the current response in the form of voltage. To do this, we need DAC to set various voltages and ADC to measure the voltage. Our microcontroller has built-in ADC and DAC. However, we used external ADC and DAC to achieve better accuracy. In this case, we connect the ADC and the DAC through I2C protocol. Timing is also crucial, as scan rates and reading voltage must be precise. Therefore, we also employ timers in our Potentiostat down to milliseconds. Last but not least, we also need to communicate with the device. We used UART protocol to communicate with the Potentiostat and buttons for a shortcut. That's for the peripheral. Now let's move on to how we approach the programming. We used interrupt-driven programming because not all the hardware would be used at the same time. Interrupt-driven programming works like this. Suppose the code runs normally just blinking LED, turn on, wait, turn off, wait, and repeat. When an interrupt is triggered, the microcontroller would stop the current code and execute the interrupt handler code, then return the previous code after it's finished. With this approach, we use the loop as the checker if there are any changes invoked by the interrupt, and execute certain code when needed. That way, the device can work more precisely and adaptively. Best of all, this strategy keeps our interrupt service routine incredibly lean, reducing stack size and preventing system crashes. Moving on to communicating with our devices. We use UART-driven interrupt to perform communication. When a character arrives, it would be stored in a buffer, which then would execute a callback function when the buffer is full. To make the device parses our command easily and simply, we design the buffer by assigning a number for a function and device parameters separated by delimiters. This is the structure of our buffer. When the buffer starts with a number, the buffer would be parsed to set the parameter to the device. For example, when we want to do cyclic voltammetry, we want to set the initial, final voltage, and its scan rate. This is where we set the parameters. On the other hand, when the buffer starts with a delimiter and a number, it would be parsed to do certain tasks, such as start the measurement, check the voltage, and so on. The callback function would not be invoked if the buffer is not full. Therefore, we make double delimiter add the end as the condition to manually invoke the callback function. This is our UART interrupt handling code. The incoming data is stored in a buffer and would execute the callback function when it's full. However, we also add another condition to execute the callback function so that we don't have to wait for the buffer to be full first. The callback function would check if there's any incorrect data in the first entry of the buffer. If everything is okay, it would change the state that the data transfer is complete. The loop that we previously mentioned would check if the transfer is completed. If it's complete, it would execute the handling function that parse the data and execute the command or store it to the memory. That's how we give command to the devices. Now let's move on to the timers. Because we need to set and read voltages at precise intervals reliably, we use hardware timers to do the job. Timers would trigger an interrupt the exact moment it hits that target count. We employ 2 dedicated timers for setting up and reading the voltage. This way, we can set the buffer time between setting and reading the voltage, which would provide us more flexibility during the measurements. This is how we perform measurement in general. First, we send the setting data to the device. We use a delimiter to separate the parameters and store it in the memory. The DAC sequence is then mapped based on the parameters to set the DAC value later during interrupt. Once we give the command to run, the execution sequence starts, activating the hardware timer for the DAC, waiting out our buffer window, and starting the ADC timer. When the first timer interrupt is invoked, it would update the DAC value. Meanwhile, another interrupt timer would read the voltage and send the voltage data through UART. We structure the output as a JSON string. This way, the output data can be processed and plotted more easily through JSON parsing. This loop repeats until the end of the DAC sequence is reached. We also program a button to start and stop the measurement to make things easier. There are other functionalities in our Potentiostat, but that's how we program it in general. Let us know your thoughts. Thanks for watching, and see you in the next video.